So far we've made a connection between pressure and microscopic quantities. And that was quantities. And that was that pressure is caused by the collision of gas molecules with off the wall of the container. It comes in with some speed or velocity vi, comes out with some velocity df. The change in the velocity is an acceleration, which requires a force from the wall, and then therefore, by Newton's third law, the molecule is exerting a force on the wall as well. And that is where the pressure comes from. And we were able to derive this formula. P times V is equal to 1/3 times m times v squared averaged. That's the average squared speed. Or sometimes called VRMS squared. Okay. Now, a second thing we want of our goal was to determine how temperature is related to the microscopic properties. So what does temperature have to do with this? That's pretty straightforward. I can just use the ideal gas law, PV equals NM/RT, and plug that in. So I get NM/RT is 1/3 m v squared averaged. Okay. Again, this m is the mass of one particle, one molecule or atom. Okay, let's do a little bit of, sorry, and I lost an n. There should be a number of molecules here. Number of molecules? Number of molecules. Okay. All right, so let's do a little bit of algebra here. I'm going to solve for v squared. So v squared averaged is going to be equal to 3 number of moles are T divided by m times n. Now, to go a little further, remember that the number, n is the number of molecules. That's the number of moles times Avogadro's number, Na. Right? So, number of moles divided by n is 1 over Avogadro's number. So I get here 3 RT m times Avogadro's number. Right? So I took here the nm divided by n, that's equal to Avogadro's number, Na. And then, next thing, what is m times Na? So m is the mass of one molecule. Na is Avogadro's number. So that's, if I take the mass of one molecule times Avogadro's number, that's the mass of one mole, right? So this is 3 RT over the molar mass of the gas, mass of 1 mole. And so I'm able to get this formula here. V squared is 3 RT over the molar mass. And you might see it written like this, VRMS. Let's take the square root, 3 RT divided by m mole. Notice what this formula has done. Really, really amazing. The left side is the speed of the molecules moving around in the gas. That's something you cannot measure by eye. And everything on the right side is something you can measure with macroscopic instruments. So this whole thing is measurable. So you can learn from this model how fast are gas molecules moving by doing measurements like on your tabletop, right? So we're able to learn how fast gas molecules are moving by doing measurements on the gas. And without looking, you don't need a microscope to do it, you can just learn how fast they're moving from this formula. As a simple application, maybe you've never thought of it before, but how about the air molecules in this room, the room that you're sitting in? Let's say it's nitrogen, so nitrogen has a molar mass of 28 grams per mole. On average, how fast are those things moving? So maybe before you dive into the calculation, take a moment and guess which one of these you think is the right answer. So just roughly from intuition, how fast do you think air molecules are moving around? And then try to work it out using pen and paper and the formula from the previous slide to determine which answer is correct. And lastly, I want to just review this one other way. So let's look at it one more different way. And let's do the same thing that we did before, PV equals NMRT. Or if you go back to the beginning of the course, you can write it as NKB times T. So KB was Boltzmann's constant. And so then combining these formulas, I get NKBT is equal to 1/3 M N V squared averaged. And the M's cancel. Sorry, the M does not cancel. The N's cancel. So the N's cancel here and here. Okay, let me put the 3 on this side. 3 kBT is equal to mv squared averaged. And then I'm going to do something which seems kind of surprising, which is going to divide both sides by 2. And why do I want to do that? Because what you see here, 1/2 mv squared, should remind you of something from your past. So this is kinetic energy, right? It's the average kinetic energy of a molecule. Because kinetic energy, K, is 1/2 mv squared. So the average kinetic energy is 1/2 m, the average speed squared. Okay. So what I have now is this interesting formula. The average kinetic energy of one molecule is 3/2 times the number, which is Boltzmann's constant, times the temperature. And that's really, really important. So that tells us that temperature, what is temperature? It's a measure of the average kinetic energy of a molecule in the gas. Okay, so if the gas molecule is moving faster, the temperature's got to be higher. Okay? If I increase the temperature, I'm increasing the molecule's kinetic energy. If I'm decreasing the temperature, I'm decreasing the molecule's kinetic energy. So that's really what the microscopic interpretation of temperature, that's what it is. It's a measurement of the energy, kinetic energy of the molecules. And then we can learn about the speed of the molecules by, just like in the previous slide, remember that the kinetic energy of the molecule is 1/2 m times the speed average squared. Okay. So here's a concept quiz on the things that we've just learned. So this room is filled with air which has oxygen and nitrogen molecules. Which of these has the greater average kinetic energy? And in case you don't know, oxygen is slightly heavier than nitrogen, so here's the masses, the molar masses of those two. So in this room, you've got oxygen molecules which are slightly heavier than nitrogen molecules. Both are bouncing around, and I want to know which of them has the bigger average kinetic energy, oxygen, nitrogen, or is it both the same? So this will be something that try and think about it, reason it out for yourself. I won't tell the answer here, but make sure you can answer this and understand it before finishing. So just to summarize what we've done, we treated a gas as a bunch of sort of billiard balls bouncing around, hitting each other, hitting the walls. And we have a new picture now, which is that pressure is due to momentum change momentum change of the gas molecules in collisions with the wall. And then we learned, I guess maybe let me summarize this with a formula. We were able to get this formula. PV is 1/3 m times n times v squared averaged. This m is the mass of a molecule, and this n is the number of molecules. And then the other important thing we learned was that temperature was related to the kinetic energy of the molecules. And a very important formula there was that the average molecular kinetic energy was 3/2 kb times T. And you can also learn about the speed of the molecule by just doing 1/2 m v squared averaged. So we've succeeded in accomplishing our goals. We created a simple model of an ideal gas, worked out the consequences of that model, and now we have microscopic versions of pressure and temperature as relating to what the molecules are doing on a microscopic level. So now the thing that remains is we have to think about, what does entropy mean on a microscopic level? We haven't yet touched on that concept, and that's where we're going to go next.